Mm. Okay, so good evening, everyone. So this is going to be the second tutorial session for the NPTEL course on finite element modeling of welding processes. So in week two, what we have what the lectures discussed was continuation of some of the welding processes and introduction to the fundamentals of finite element method. Yeah, just to save bandwidth, I'll just turn off my camera and yeah. Okay. So essentially, the introduction was complete, vehemently mathematical. So if I just pull up the lectures, so I think these are the lectures here. So essentially, it introduced the why do we need finite element method, because most of the problems happen to be non-solvable analytically. So we have to adopt numerical techniques to solve them. And it was also introduced of the different types of analysis, second 2D and 3D. And the instructor also introduced different types of elements that are typically used. However, this is not an exhaustive list uh, based on applications, and as per the situation demands, we introduce different types of elements also. So if you are solving some plate-like structure, then we use plate elements, and if we are solving some shell-related problem, then we would be using shell elements. An introduction about this two-dimensional analysis. So by this, I mean, with this way, we cannot actually understand finite element methods. So what I'll do is I'll just take you through the finite element method by solving an example problem that we'll be doing now. So, I just plan to start uh, to solve a problem called as I'm sure this must be very familiar to you, a uniform bar extension problem. So essentially, the problem goes as and then I would be introducing every concept one by one. So say we have a bar extension problem. So given a structure like this happens to be a bar, and either we can have some sort of say, right now I'm taking to be a uniform bar, right? So this happens to be say uniform, which means that we require the quantities E and A are constant throughout, and these are X direction. And E here is Young's modulus. And A is the area of cross section. Or either we can have say some yeah, this is some distributed load, and what I'll do is I'll put it somewhere for here, and say we have some concentrated load here P, and some distributed load say F of X, and the length of this bar is say L, and these are origin. The left hand side is fixed. So we want to say solve this problem using finite element method, and then we'll just every term we'll introduce term by term whatever is required. So say the governing equation of the problem governing equation of this problem is EA. Ideally the governing equation is given by, for a general bar extension problem, as d by dx of EA, which can also be a function of x. AE can be a function of x. A also can be a function of x. And then we have du. So here u actually indicates uh, the displacement at every point x. Okay. and is equal to say some f. So this is what, and this f would be f of x. This is our distributed load. So let me give you the, let's talk about one term by term. So this happens to be what we call as uh, the distributed force, internal force. Actually, this is internal force. And this is the external distributed force. And now you would ask, okay, but even P happens to be a load. So where does where is P incorporated? So P actually goes into as a bond as a subject to. So say at this end, since this is a 1D problem, and the order of the differential operator here happens to be second order, right? Since it will involve the highest order derivative will be 2. So as per the theory of elliptic operators, we require 2 boundary conditions to pose this problem as a well posed. So that's why we require 2 boundary conditions, one of which is very much evident from the setting of the problem. This happens to be u at is equal to 0 is 0. And the second boundary condition is u of a, x and L du of x at x is equal to L happens to be P. So this is where our what we call concentrated load goes. Concentrated, or we can even call it terminal load. Okay, so this is the general setting of this problem. So before this, let's first start it. Let's first try to develop finite element methodology to solve this problem. So what I'll do is, let me write the problem here again once more. It's d and so d by dx of e of x, a of x, du of x is equal to f of x, right? And it was subject to the conditions that u of x is equal to 0 is 0, and e of x, a of x, du by is equal to at x is equal to L is P. Now let's start systematically uh, build up the FEM methodology here. So at first, what we do is we first define something known as a solution space. Yeah, please interrupt me if you find some dots here and there. To solve this problem, first we define what we call as a solution space. So solution space is as is very evident from its name, it's the vector space in which one member, one or even more solutions lie. Okay. So in this case, how we define the solution spaces, we take it to be, say, S is equal to, now it's a set, we call it U, such that U of at x is equal to 0 is 0. And this is a very rudimentary this one, but we first must also define what do you mean, what is U here? Essentially, let us make it more mathematically rigorous. So we'll call it U is a member of whose at least the first derivative must be continuous. So U is an element of C1, which is defined over 0 to L, such that U of x is equal to 0 is equal to 0. So which means that if you have U as a function, say any U, U must be continuous, and du of dx must also be continuous. So this is the first requirement on the members which form the solution space. You may ask, but why do we impose just one this condition for member of the solution space? Yeah, the answer is that we always want to have only those conditions what we call as the the Dirichlet boundary conditions. So in this case, this happens to be the Dirichlet boundary conditions. There could be many more questions that what do you mean by Dirichlet Dirichlet conditions, and what is the what are non-Dirichlet boundary conditions, right? So the thing is, Dirichlet boundary conditions are those conditions which actually follows from the geometry. So this will follow from geometry of the problem. Like you see clearly here that at the left end, this bar is actually fixed. So there are no displacements is allowed at the left end. So that actually follows from geometry. And the other condition, which what we call as the Neumann condition, is a boundary condition which actually follows from, which actually happens to be what we call as the force-like or force-based boundary condition. So something that which resembles something which actually enforces some causation mechanism, right? So that is what we call as Neumann condition. More appropriately, we actually get this boundary condition by from the calculus of variations. So right now we won't be discussing all those ideas. So I'll just keep it at that. However, a simple trick to determine which is a Neumann and which is a Dirichlet boundary condition, we have one say a simple approach. So say given any nth order, say nth order operator, fine, any operator, nth order operator, this say happens to be a function of y prime, say y not fine, just let me write d by dx. This is just a digression, so I'll just erase it once the system, and d square y by dx square, likewise still n minus 1 y by x n minus 1. So see, this is our differential equation which we need to solve. Now you may ask, okay, but which are the Dirichlet boundary conditions? Which are the Dirichlet boundary conditions? Because the thing is, this equation, for it to be well posed, we require n boundary conditions. Okay. Now, which are the Dirichlet and Dirichlet boundary conditions, and which are Neumann boundary conditions? I'll just call it BC. And mine is from the elliptic theory of operators, that n must be even. And this usually happens for mechanical problems, that n always tends to be even numbered. So which means that we could also frame this as say, okay, just I'll just call it. We can also frame it as n is equal to 2m, since n happens to be an even number, right? Now for Dirichlet, I'll just call it D. There are m boundary conditions, m number of BCs, and it starts at y of something is equal to something. Likewise, the derivative of y at some point is given some value, and it must always be either right or the left end, isn't it? Since this happens to your one-dimensional problem, because the only running variable or the independent variable is x, so it will go from x is equal to say some x1, right? So it could be at x no x, what do you call? I'll just call it x naught or x1. So this y could be at x is equal to x naught or x is equal to x1. Likewise, this goes till d of at m minus 1 by dx m to the power n minus 1. So this means that m minus 1th derivative of y at either x is equal to x naught or x is equal to x1 will also be assigned some value. So these are the collection of Dirichlet boundary conditions. For Neumann, it is the others. This full starts at mth derivative to 2m minus 1th derivative. So those values will be called as the Neumann boundary conditions. These are just a simple trick to decide which is uh, Dirichlet and which are Neumann boundary conditions. So I'll just erase this. And likewise, if we extend it to higher dimensions and provided that we have an elliptic operator, then it will extend in all the independent coordinates that we choose, or the problem, or that the problem is actually based in. Fine. So coming back to our solution space. So the vector space in which one or more solutions lie is what we call as the solution space. And this will only contain all the requirements are stringently applied, which follows from the Dirichlet boundary conditions. Now we also define something known as what we call as the variational space, or it's also called as the test space. So these are usually the vector space. This is the vector space from which, or which contains weighting or test functions. The theory of test functions has a variational meaning, but since this course is not meant for that, well, let's just call it test space, and we'll later see what this test function actually mean. And here, what I'll just call it a set V. This also happens to be a set of functions V, and let it also be of the same collection. So it also belongs to the set of functions which are which are whose first derivatives are continuous. Okay. Right. And then u of this will be v of x is equal to 0, also happens to be 0. Right. A more stringent requirement could be that we take, instead of C1, we'll take it L2, which is square integrable functions, but let's keep it at that as of now. So since we have defined our solution space and the variation space, all that we need to do is let's start building our process. So we first, what we call as, let's derive weak form of the governing equation. Now, what do we mean by weak form? So since there is something known as a weak form, so from a logical perspective, there must be something called strong form, right? So this is what we call as a strong form. Now the question arises, what do you mean by strong form? So if we take a look at this equation, there are only derivatives involved, right? And you know that derivative is very much a point property, that we require a point and a very immediate neighbor to define the value of derivative. So which means that this simply implies that this condition must be met everywhere, or must be met at every point in the domain. So this is what we call as what we mean by strong form. So strong form simply means that we require it to be satisfied at every point in the domain. However, due to certain limitations, we cannot actually satisfy every, when we numerically solve, we cannot satisfy, or to derive a numerical solution, we cannot use the strong form, which means we cannot satisfy this condition everywhere. So we will be looking at certain functions, or we'll be looking at solutions which will not satisfy in general. It won't satisfy this equation pointwise. Fine. So that's what where we call as we derive something known as a weak form of the equations. In order to derive the weak form of the equation, we will have d of dx as a function of e of x, a of x, and du of x. I'm just writing it for the sake of mathematical clarity. And then we'll bring f of x to the left hand side and then equate to 0. Now what we do is, we know that U is an element of solution space, because that's how I define the solution space S. Let me call this S here like this. Let me call it V. Right? U is an element of S of solution space S. Okay? And this needs to be determined. However, before that, what we do is, now from this equation, what we see that if this equation is fulfilled at every point, the resultant is always 0 on the right hand side. So it means that given some output, some input, the output and the system deformation or the solution will be satisfied so that we always have something on the right hand side of 0. Right? So this is something like what we call as the remainder, or we can also call it residual. Right? So the other way what we do is, let's just multiply. Right? So we multiply both sides by v of x, right? So once we multiply by v of x, and so we'll just call it v is a solution of v, isn't it? So now the thing is, this is what we call as test function. This is a test function, right? Now, once we multiply both sides by v, so this will be d by df of e of x, a of x, and du of x by dx minus f of x, and this we multiply by v of x, and then also integrate over the domain. So, and which means that we have x start from 0 to L, and this likewise 0 into v into dx, right? So this will eventually come out to be 0. Right? Now what we can do here is, let us have something known as, we can just break it up into two integrals. So E of x, let's just call it EA. It's provided that we understand the meaning. D of x minus 0 of f of x, v of x is equal to 0. Now here, what we can do is we can use integration of parts. And you will ask, okay, what do you mean by integration of parts? So integration of parts is integrate by parts. Is when say you have a function u prime, right? Yeah, u prime v dx. This gives us so the first this is actually integrated. So you have u v at some, say if it's 0 to L, then it will be 0 L minus, likewise we'll have u v prime d of x from 0 to L. So let's use this idea here. So here this term happens to be u, or I'll just call it something else. So let me call it f prime g d of x is equal to fg minus f of g prime dx, right? So it means that if we compare it, this happens to be f and this happens to be g, right? So that means that what we have here is, we'll expand it, and then f of g means ea du by dx into v, right? 0 to L minus 0 to L ea du dx dot dv by dx minus 0 to L f of x v of x is equal to 0. Fine. Now what we do here is come back here again, and slightly let's rearrange this such that uh, okay, it seems there is some issues here with our signs. I'll just correct it. I'm sure it won't be any creating any problem, but just to this 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 will just help us to correct. I mean, we'll see it why we need to do this equal to 0, right? So essentially this will be plus, and we'll see why we are doing this. Okay, so this is plus, right? So actually this helps us to so this term here will go on the right, or otherwise what we'll do is we'll slightly rearrange so that we have integral of 0 to L ea du by dx dv by dx is equal to integral of 0 to L f of x v of x d of x plus, right? Now you see that this term will go on the right, and then we'll just transpose everything, or we take something known as a reflection about u is equal to sign. So this gives us ea du by dx into v 0 and L. Fine. Now what we do is, now let us use the conditions on u and v. Recall that u had to satisfy at x is equal to 0 is equal to 0, and v had to satisfy the condition which is v of x is equal to 0 is 0, And likewise, you also had to satisfy this relation, right? So what we do is, let's look at this term here. Here, v of 0 is equal to 0, right? And for what we'll do is, let me just expand it. This term is equal to e of a du by dx v at x is equal to L minus e of a du by dx v x is equal to 0. Mind you, from the conditions that we have, what we have is v u is equal to 0 at x, u is equal to 0 is equal to v is equal to 0 at x is equal to 0, and e of ea du by dx is equal to p at x is equal to L. So we'll use these conditions here. So what we get is, this term actually goes away since v is 0, and we will be left with this term. Let me write it again. This becomes 0 to ea du by dx to dv by dx, right, is equal to integral of 0 to L f of x vx dx, and what we call plus p into v, and v has to be x is equal to L. So this is what we have as the weak form finally. I mean, essentially, we had already obtained our weak form here itself, but this will be the eventual weak form, which we'll be using for our purpose. So this is the what in operational sense, this is the weak form. Okay. So now we have obtained one aspect, right? So this we have obtained as the weak form. Now what we do is, now in order to solve this problem, now we may require to discretize the problem, since we need to solve this problem numerically. So we will discretize the domain. This is the second part. Actually, we are moving in two parallel lines, and then uh, as of now, we are doing these things parallelly. Then we'll have to merge both these ideas. Fine. In the discretization of domain, what we do is, we have this domain 0 to L. Now it's just a straight line here, right? And x equal to 0. This x equal x is the x direction. So what we will have is equispaced. As of now, let's deal with equispacing. So this will be x equal to, say, some x1. This is x is equal to x2. Likewise, essentially, this will be x is equal to L, which is essentially x is equal to xn, small n. And let's call it small n, right? Now, which means that, just to clarify this, what I mean here is, we have, say, length of the domain is L. Fine. Now what we do is we break it down into segments, or what we call as elements, right? Of equal width. And so the width here happens to be, so first of all, let's decide how many number of elements we want. So this is one element. Second, likewise, this is the nth element. First, second, and nth element. So it means that the width will be h is equal to 1 by, or L by n. Right? So essentially, initially our problem happened to be a continuous domain. Now what we have done is we have broken it down into n elements, and that is where the name of this method comes, finite elements. And once we have the width, Now what we can have is, now we can have some, these are called as nodes. So the ends of every element are called nodes. So it means that x is equal to xi is equal to I into h, where I runs from 0 to n. Okay. So which means that we have n we have sorry we have plus 1 nodes. Okay. And n elements, as I have mentioned already. Fine. Now once we have discretized the domain, now let's consider one domain at a time. Say one element at a time. Now pick an element I think before that what we should do is let us define something known as a basis functions, but before that let me first define what we call as the basis functions. Basis or even shape functions. Now the idea of basis or shape functions is that, say we have this discretized domain here. Say this was xn and this was x naught. So we require certain elements, I mean some basis functions, such that it will have a value of 1 at the node and 0 at other nodes, right? So something like this. So this is n naught, because we don't have anything on the left hand side of x naught, so it is just it looks only half. And here n1 is complete. Likewise, this is n2. So similarly, it goes on and on till here also. So say we have some xn minus 1 here. So this will bar n minus 1. Not yeah, this n minus 1, and then we have other one which is the last, for the last node we again have a half basis function in appearance, n minus 1, and this is of n. Right. Okay. So this elements has some property that any ni, provided that this is xi here or this is node xi, then ni has this property that it is 1 at x is equal to xi. Fine. So what we do here is, and at x is equal to xy, and it's 0 at x is not equal to xy. So this is the requirements on the shape functions. And we use this to construct what we call as, using this idea, right, what we can do is we can actually express the domain, and we'll clearly see why and how. We can clearly use x is equal to summation of But I'll just start from the beginning here. I mean, before using summation, let's start building this. You know that x is equal to x naught into n naught of x. Likewise, x1 of n1 of x plus x n of n. Now you'll see, okay, but why are we doing this? You see, if we have the say if x is equal to x naught, this implies that what happens on the right hand side, left hand side is just x naught, x, and then on the right hand side we have x naught and naught of x naught plus x1 and 1 of x naught plus xn of x naught, right? So this is equal to 1, and from the property this is 0. This all these n's are 0 at x equal to x naught. This is what it confirms. I mean, you can see how this property is being used, right? So which means that, and we can simply write x is equal to summation of xi and ni of x. This goes from 0 to n, right? Fine. This was to use for geometry purposes, or to describe the domain essentially. Description of domain. What we do is we also use it to even define our values, or even the solution as well. So u of x is defined as summation of s equal to 0 n, and then we are also using something known as ui, which means that these are the values of u at ith node and ni of x. So we use the same basis functions. This is the beauty of this method, that we use the same basis, and as well as for v is also I is equal to 0 to n vi ni of x, right? So what we do now is go back to our equation here, and I'll just copy this and paste it here. Mm, mm. Now what we can see here is on the even for the both the terms on the right and the left, we can actually break this integral into sum of integrals. It's like x is equal to x naught to x1 ea d by dx plus x is equal to x1 to x2. Mind you that integration is just the sum of multiple integrals. It can be defined like that as well, provided that the domain or the limits of the integration happens to be continuous. Plus till it will go to x is equal to xn minus 1 to xn, and the same thing dv by dx. Likewise for the term on the right as well. Uh, we'll have x is equal to x naught to x1 f of v, f into v dx plus the same thing, x to the n minus 1 to xn f v of dx. And for this term, we'll just have p into v at x is equal to xn, right? This was, yeah, this is what we have done now. And what we can do is, what we can do here is, uh, you know that what will happen is there are multiple ways of proceeding from here, but let's just choose one. What we do is, can we not have the, I'll pose this question, can we not have an approach where we do not have to carry out all these integrations? Yeah. And you can clearly see that depending on n, as the larger the number of n, the more the twice the number of integrals we have, and that becomes very complicated. So that's why we would like to find a way or seek a way where we may have to, we'll have some systematic way of doing integration so that uh, all these integrations can be performed very simple using some templates, right? So let's do that. Then now we just proceed from here to describing something known as an isoparametric element. And I'm sure this you may have come across what we call as isoparametric element. More clearly, 1D isoparametric element. Right? Okay. So now what we do is let's introduce something known as a parent element, which has just two nodes, this node as well as this. And this, we are using some xi coordinate. So this is xi is equal to -1 and this is xi is equal to 1. So that it's obvious that the center point will be 0. So we will map this. This is called as a parent element. This will map to some mapping function phi to one element of our domain. It's xi psi plus 1. Or to be more clear, it's xi to xi minus 1 because that's how we have named our domains, right? Xi to xi minus 1 to xi. So this is what we call as the physical element. And now we need to first define this mapping function, right? Before that, what we do is we'll also have some sort of basis functions like the one we had defined there, but for this parent element. And for now, let's just deal with linear elements. Let me use a different color to red itself. This, yes, fine. This is n1, n hat, let me call it, to differentiate from n. And this is n hat 2. Both is function of z and z. So here also it will have the similar condition on that n of I hat of z is equal to 1 if z is equal to zi, 0 if uh, I think I'm sure. Please do not get it mistaken here. We are only looking at the nodal points. Fine. Okay. So likewise here. So using this method, what we can do is we can have some sort of a mapping here. What we'll do is we'll have x is equal to, let's map to a, since we are using some mapping, right? So this is p, x is equal to, let me call it x is equal to phi of xi. This happens to be a function of xi minus 1 n hat 1 of z plus xi n 2 hat of z. So we are essentially mapping this point, point 1, to here, to this point. So this is what we are doing. And we can clearly see that, say, if xi is equal to minus 1, then this term will be 1 and this term is 0. So it means that we get x is equal to x. We recover x is equal to xi minus 1. Likewise, if xi is equal to 1, then this term is 0 and this term will be 1. So it will be xi is equal to xi. X is equal to xi. Fine. Fine. So once we have done this, now we need to construct. Let's construct n1 hat of z and n2 hat of z. Based on the requirements, which is given here, we need to build functions, right? What we'll do is n1 hat of z will be such that 1 minus z by 2. We can easily arrive from this equation here as well, but just to save time, let me just write it n1 hat of xi is equal to 1 minus xi by 2. Likewise, even n2 hat of xi, and here let's check whether the conditions are met. So say if xi is equal to minus 1, then n1 of hat minus 1 is equal to 1 minus minus 1 by 2, which is 2 by 2 is equal to 1. Fine. And if xi is equal to 1, then n hat of 1 is equal to 1 minus 1 by 2, which is it. This means the conditions are fulfilled. Likewise, n2 hat of z is equal to 1 plus z by 2. And we can clearly verify that when xi is equal to 1, then 2 by 2, which is 1. And when xi is minus 1, then 1 minus xi is by 2 is equal to 0. Those conditions are fulfilled. Okay. Now we have, once we have this, so I can clearly write is equal to, no, let me write as x, x of z is equal to xi minus 1 into 1 minus z by 2 plus xi 1 plus z by 2. Fine. So, fine. And we will use the same basis functions to even construct u of z, or I'll just call it not u of z. Let me call it, since u happens to be a function of x, which is again a function of z. So let me u of x of z is equal to ui minus 1, 1 minus xi by 2 plus ui. Just a moment. Sorry for the delay. Yeah. So we'll be using ui of 1 plus z by 2. And since we use the same mapping functions or the same shape functions to express the geometry and solution, that's why we call it isoparametry. Means we use the same parameter to define geometry as well as the solution. Right? Now let's go a bit ahead, and then what I'll write here is, since we know that maybe just better to copy it. Mm. Now, since we have this, now let's try to find its differentiation with respect to z. And this is not very hard, since xi and xi is minus 1 are constants. So this into minus 1 by 2 plus xi into 1 by 2, right? So this gives us xi minus 1 by 2, which we recall from our geometry here, that this is equispaced domain, isn't it? So any xi, say if given that we have x1 minus x naught is equal to h, x2 minus x1 is also h, so likewise, so we'll just have this to be h by 2. Now this du by dz is also equal to, okay, not first for at first let me have du by dx, isn't it? This will be equal to du by dz dot dz by dx. Now du of z is very we can easily find from here. So it is ui minus 1 dot minus 1 by 2 plus ui . isn't it? But let's just for the sake, let's keep it at it as it is. We'll see why I'm not doing, because it gets very cumbersome to perform this letter. So let me just keep it, provided that we have already known that this is nothing but ui minus 1 into n1 of c n hat plus n2 hat plus u I n2 hat of z, isn't it? So this is nothing but ui minus 1 n hat 1 prime plus ui n2 hat prime of z into, and this can written as 1 by dx by dz, and this we can clearly see that it's nothing but uh, h 2 into h. But for now we will call this term as j, which is the Jacobian of mapping for simplicity. So I'll just make it more prominent here that j is equal to d of x by dx, x of dz. This happens to be h by 2. This will use it quite a bit here. Now, so our original goal was to devise an approach where we do not have to carry out all these integrations one by one. So now what we will do is we will pick an arbitrary integral from here, any arbitrary integral, and then we'll see that we are very easy. It's uh, very easy to construct uh, find a general form of the integration, right? Say we pick up we pick any integral, elemental or say integral term for an element, or we say we pick an integral term for any element. I think that's a better way to put it. So we have same x is equal to xi minus 1 to xi, which is for the ith element. And then we have ea du by dx dv by dx into dx. Fine. Now what we see is we are clearly able to see one thing, that we can very much write it in this form, xi minus 1 to xi. And then we have ea dot du by dz dot dz by dx, dv by dz dz by dx. Likewise, you can also write as dx by dz to dz. See? So which means that we have mapped from x the integral or the independent variable from x to z. The endpoints will also change, right? The endpoints will also change. So this will be z is equal to minus 1, and this will be z is equal to 1. And we can clearly see that dz by dx is nothing but 1 by j. And this is j. This is j. This is 1 by j. This is 1 by j. So, and keeping up with the requirements that we can have an arbitrary e. So we can also have e as a function of x of z and a also as a function of x of z. So we have du by dz dot dv by dz dot. So this jj cancels one time, so we are left with 1 by j to z. So what we have seen is we have been able to use just one integral here. Based on that, we are able to determine. You have devised one template using which we can compute all other integrals. Now, I am keeping this as of now. this here that I'm taking it to be general, right? But say if you go to a particular step, so in this case, we still have to integrate it. But the thing is, we can uh, already uh, these terms are will be the same for every integral this term, isn't it? So this is where we have to apply our minds. Let's say if with our beam, sorry, the bar happens to be so that E and A are uniform throughout, then we will definitely not have this complication, isn't it? So I'll still keep it as maybe I'll still keep it as general, or or what we do is we can actually say take a different path here. Okay, but first of all, let me just collect all the terms like we had done here, like this integral here. Let's express it in that form. But before that, we may need to also determine that for x is equal to xi minus 1 xi of f as a function of x dot v as a function of x, right? Dx. So this can be mapped as, let me keep it as it is now. So f of x of z dot v of x of z dx by dz dot dz, so that our integral limits becomes -1 to 1, and we have this as j. So what we have is -1 to 1 f of x of so j is what we called as he by 2, right? So it is h by 2 z dot uh, v of x of 2 dz. Fine. So what we have been able to do is we have been able to construct or say create a template to find general integrals, general integral to general yeah, for to find general integration. Mm. Let's see. What I mean to say here is for all elements. That's what I mean to say. Now what we'll do as of now is so this is for the when E, F, A are point dependent, or say are functions of x. Now I'll just keep this space blank as of now. We'll just pick up a special case. Special case. So the special case here suggests that we have E and A and even F are constants. So this is the special case here. So what we'll do is I'll just pick up this integral here. So in this case, what happens is E and A will just be constants and will come out of the integral. So which means that xi minus 1 to xi E of A du by dx dv by dx into dx is nothing but E of A can be taken outside -1 to 1 du by dz dv by dz 1 by j into dz, and the 1 by j, as we recall clearly, is 1 j is equal to h by 2, so 1 by j is 2 by h. So this is nothing but 2 ea by h, isn't it? And then minus 1 to 1 du by dz dv by dz into dz. Fine. So we can write this as 2 ea of by h, and what we recall is uh, okay. So here let me not entangle you. So what happens is we have a choice to pick a v, since v is a test function, isn't it? We have a choice to pick v. But just before that, let me tell you something, is that we can have 2 ea by h minus 1 to 1, and recall that we had expressed u in terms of uh, u I minus 1, or no, I'll just call it that u I minus 1 to n1 of hat d by dz plus ui and 2 hat of z into dv by dz to dz, right? So this becomes 2 ea by h minus 1 to 1 plus ui and 2 hat by dz dv by dz. So as I mentioned that we have a choice to pick v, which is a test function, right? So let's start with, we take v is equal to n1 at, since it's our choice, we have say 2 choices vn. Then this gives us thing, or we can okay, I think this could be a bit more cumbersome, so why not express v also likewise? We'll call d by dz vi minus 1 n1 hat of z plus vi n2 hat of z, and this is it easy. So that we have vi minus 1 d n1 hat plus vi and d n2 hat by dz into dz. Right? So let's say this could be a bit cumbersome for to understand. So it's better to put it like this. So what we need to do is evaluate. We have to evaluate 4 integrals, which are just standard integrals, right? So you can have 2 EA by h and minus 1 to 1, ui minus 1, vi minus 1 integral from to 1, dn1 by dz. This is nothing but I'll just write the values here. n1 hat of z is y minus z by 2. 2 hat of z is plus z by 2. Right, isn't it? So we can have this as in fact, we can write this in terms of let's first write this in terms of a matrix vector product. So it is 2EA by h, and this we have VI minus 1, VI transpose. The matrix will be minus 1 to m, n1 hat prime, let me call it. Prime indicates derivative with respect to z. Likewise, n1 hat z. Similarly, we have minus 1 to 1, n1 hat prime, n2 hat prime dz. And here also minus 1 to 1, n1 hat prime and 2 hat prime dz, and here we have minus 1 to 1 and 2 hat prime and 2 hat prime dz, and this side will be ui minus 1 ui. Right, now we can just carry out our integration. So it is 2a by h right? And then we can have vi minus 1 vi transpose and to n1 prime, and n1 prime is minus 1 by 2, and then again 1 by 2, right? So it's like minus 1 by 2 whole square, which is 1 by 4, right? So it will be 1 by 4 into, and it goes from minus 1 to 1. So it's like 2. So it becomes 1 by 2. Likewise, for the second integral here, n1 prime is minus 1 by 2, and n2 prime is 1 by 2. Integral from minus 1 to 1 dz. So it is minus 1 by 4 into z from minus 1 to 1. So this goes minus 1 by 2 into 2. So this also becomes minus half. Likewise, this term is the same as that, so it is minus half. And fourth it will be 1 by 2 whole square into z from 1 minus 1 to 1. This also becomes 1 by 2. This is a simple integration since these are all linear functions. And this we can write it as ui minus 1 ui. The more simplified version would be to bring out half from the matrix, and then we'll have, and this will cancel with 2 here, so it will be ea by h vi minus 1 vi transpose. It is 1 minus 1 minus 1 1 ui minus 1 ui. So this was the space for this integration here, right? And we'll have one more integration, which is with respect to say minus, sorry, for xi minus 1 xi f of, since now we have assumed that f is constant now, so it's just f v of x, right? And dx, this is the same as minus 1 to 1. F is outside, and then v can be expressed as vi minus 1 and 1 hat z plus vi hat no, and then n2 hat, likewise dx by dz, which is j2. So this is h, right? This becomes h by 2, z by 2. So all that we have is f of he by 2, and then there will be two integrals, vi minus 1 minus 1 to 1, and hat is 1 minus z by 2 into dz plus vi of 1 1 plus z by 2 dz. Yeah, so say if you have this triangle whose base is 2 and height is 1, you clearly know that the area will be half into base into height, right? This is 1, and we can even verify that that's how it should be. So the integral is say z by 2 minus z squared by 4, 1 to 1. So this is an even function, so this goes out, so we'll be left with 1 plus 1 by 2, and we clearly see that it's equal to 1, right? So essentially we can write this in terms of vector matrix vector product, or some vector product is f of HC by 2, and we can have vi minus 1 vi transpose, and here we'll have 1 and 1, and we can clearly verify that both these integrals will be the same actually, and it's just this will be the other triangle, isn't it? Yeah, so this is how it is, right? And so now we have been able to derive the integral of this quantity and also this quantity. So all we are left with is assembling it. So what we have done so far is, these are known as elemental matrices. So this here is known as elemental matrix, or otherwise, let me just write it here, elemental stiffness matrix. We'll call it as K defined for element E is equal to EA by H, right? EA by H, and then 1 minus 1 minus 1 1. And elemental force vector is F of E. This matrix, this vector. This is F of H. There is no E here, as we're not having trouble, since we are assuming that H is constant already. And fine. So F of H, F into H by 2, and this will be 1 1. Okay, so the next process here is what we call as determining assembling the global matrix actually, or assembling the stiffness matrices to form a global matrix, right? Now you'll ask me, okay, but why are we doing this? What's the purpose behind this is? The thing is, when we are integrating it, we only considered one element, which is from xi minus 1 to xi. Now we have to incorporate all the elements, which x naught 1 till xn and xn minus 1. So all these elements we have to incorporate in a single matrix form, and then we will be able to solve this equation, right? Okay, so let's start with element 1. So element 1. So this was EA by H. This was V naught V1 transpose 1 minus 1 minus 1 1, and U naught U1. Element 2, it was EA by H. Uh, uh, mm, okay, but first of all, let me go back to the equation. I think that we are missing something. Okay, so clearly, uh, okay, let it be like that. Yeah, we'll fit it later. The boundary condition is fine. This will be V1 V2 transpose 1 minus 1 minus 1 1, and this will be U1 U2. And likewise, element nth is EA by H Vn minus 1 Vn transpose 1 minus 1 1 minus 1 minus 1 1. And Un minus 1 Un. So you clearly see that there are many things which are repeating, since element 1 and 2 will share the first second node x1, right? Which means that when we are assembling, there will be at some certain nodes there will be contributions from both the elements. So the global matrix element global stiffness matrix. For now, let me write the global stiffness matrix will be I'll just call it global assembly, and then we'll define what is global stiffness matrix. Global assembly is will have EA by H, and then this will contain V naught V1 till Vn transpose. And here let's start. We'll have 1 minus 1 minus 1 1, and the rest zeros. Since we are having here, we'll have U naught U1 to Un. And then what we'll have is, since there is U1 is being shared by both these elemental expressions, so to speak, then we'll have 1 plus 1, and we'll have minus 1 minus 1 1. And likewise for the third element, we'll have 1 plus 1 minus 1 minus 1 and 1, right? And likewise, it goes till here. Minus we'll have for the last element. For the second last element, we will have un minus 1, which is being shared. It is 1 minus 1. Uh, minus 1, 1, 0. And it will be 1 plus 1 minus 1, right? And here it will be for the last element is 1 plus 1 minus 1 minus 1 and 1. Essentially, this is what our global assembly gives us. Now let's carry out a similar exercise for our force vector assembly. So we know that we have F for element 1. We have the expression is F of H by 2 and V naught V1 transpose 1 1. For element 2, F of H by 2 V1 V2 transpose 1 1. Likewise for element n we have F of H by 2 Vn minus 1 Vn transpose 1 1. Now let's assemble it. Let's assembling global assembly. So here it will be a bit straightforward. So FF by 2 and then we'll have V0 V1 till Vn transpose and now let's start building. For element 1 we have 1 1, but for element 2 we'll have 1 plus 1 1. Element 3 1 plus 1 1. Likewise for nth minus 1 element we'll have 1 1. It will be plus 1 here from the before one, and then we'll have for the last element 1 plus 1 and 1. So our global assembly remember that we have one more term here. We'll adjust it. I mean, fit it into the equation now. The global equation or global matrix equation. So we'll have EA by H V0 V1 till Vn transpose, and then here we have 1 minus 1 minus 1 2, and then it goes to 2 minus 1 minus 1 1, and this one will be u0 till un, and this is equal to f of h by 2 v0 v1 till vn transpose, and this will be 1 2 2 last. Now we have one more term which was pv at x is equal to l, isn't it? So here what we have to do is we can write it as p v at x is equal to l. This can clearly be written as p into the v0 till vn, since vn was what is represented here, and you can write 0 0, and only the last element will be 1. So this is how we fit it here. P v0 to v1 something like till vn transpose 0 0 till 1. Fine. So this was our global assembly. Now what we do is now substitute, or we use some principle from since v is arbitrary, we can put say any v is equal to such that we can take any value of vi's. Right? So in that case, say when we have v naught is equal to 0, which is obviously it has to be 0 will from the boundary conditions. So for rest of the cases, why not we put the values right now itself? Okay, so let's do something right away. Why to waste our time? Maybe more systematically. Before that, substitute BCs. From BC, what we have is u of x is equal to 0 is equal to 0. This implies that u naught has to be 0. Likewise, v of x is equal to 0 is equal to 0 implies that v naught is 0. Right? So which means that we are able to so having the first row and the first column doesn't make sense because it's anyway going to be multiplied throughout by 0. So we can just remove v naught such that we'll have ea by h, and it will be v1 till vn transpose, and likewise for matrix compatibility we'll have 2 1 2 minus 1 minus 1 2 till 1 minus 1 1, and here also we'll start with u1 till un. This is equal to f h by 2. I hope so, yeah it is. And then we'll have v1 till vn transpose, and then u and then what we'll have is 2 till last will be 1, isn't it? Yeah. And likewise even for p we'll have p v1 till vn transpose, and it will be 0 till last element is 1. Now since v is arbitrary, it can take any value of vi, and what they call, and so which means that taking vi to be 0, starting with sorry, vi not equal to 0, and others 0, for I is equal to 1 till n, we can have, now we'll have this matrix form ea by h, and 2 minus 1 minus 1 2 minus 1 1 minus 1 1, actually 2. This is what our system is, fh by 2. Let me call it, write it nicely. That's by 2, and then it will be 2 2 2 and 1 plus p 0 0 and 1. So this is the equation we have to solve. So this is our equation to be, or matrix equation to be solved. Okay, so well, since we have established the finite element equations, which has to be solved, so in the next class we will actually code it and solve it numerically, or will let me frame it. We will solve it, solve the matrix system, because that's anyway a numerical problem, and compare with analytical solutions. That is first job. And the second job would be we shall also generalize the method, the approach for arbitrary E, A, and F variation, since this is what is necessary. Okay, so this will be our task. So we will actually solve, we'll code this matrix equation either in Python or MATLAB. I will prefer Python because it's an open source software. And this can be verified with analytical solution, but for say, the generalized problem, then we'll have to rely on the numerical solution. So this is what we'll be doing with the next class. So I thought we'll do it today, but it seems that the time is already about to finish. So at least we have established the formulation clearly from the very beginning. We went step by step and then arrived at the final matrix equation. So let me just give an overview of as to what we were attempting at. So we had this bar extension problem. Then we had this strong form. We defined the solution in variational spaces, then derived the weak form. And then once we had the weak form of operational waveform, then we discretized the domain, defined the basis function when we use this isoparametric approach, where we use the same basis functions to construct the approximate the solution as well as the geometry. And then we went in search of a generic template to carry out this innumerable integrations that we have here. For that, we actually introduced the concept of parametric element. For this, we have introduced 1D isoparametric element. Then we found the shape functions, determined the Jacobian of mapping. Then we picked an integration. We were able to construct an integral term using this where the integration involved integration over the parent element. And then now it was for a generic bar with say non-uniform features. Now what if we have where E, A, and F are constants? So here we started, and then we found that every integration is nothing but all the integrations evaluates to the same integral form eventually. So we clearly see that any integral over an element eventually has the same representation post integration. And all that only which I mean the only thing that varies is the nodal values, which has to be anyway computed later. And then we did the same to determine the elemental force vector. And eventually we assembled the different elemental matrices and the vectors to form a global matrix. We did it for stiffness, so global matrix here. Then we did a global vector actually for the force vector. We have the global assembly to form a vector. And then once we have this, then we substitute the boundary conditions, determine the problem which could be solved. But before that, we also need to get rid of all these arbitrary VIs. So this we could eliminate by taking one VI to be non-zero at one time and rest to be zero. And when we're able to arrive at this governing at this discretized equation, and here this equation, this part of this equation, this part here, this is known as global stiffness matrix, and this is known as global force vector, and this is our terminal load vector. Okay, so then we outline what we'll be discussing in the next class. We'll be solving this equation and comparing with analytical solution using say code in Python or MATLAB. And then we shall also generalize the approach for arbitrary E, A, and F variation. So yeah, with this I'll be closing today's session. So yeah, I'll stop recording.